known as AKA, also known as concerning. So about or concerning the range, or just simply read the range of the transition function. What is the PDA doing? It may go to some new state, and it could write a new symbol on top of the stack, right? Those two things. Now, how am I going to get rid of this? So, those two things that the transition function delivers, based on based on the ordered triple from here, it then decides. So it'll return a member of Q, like the next state, and together with a member of this, the stack alphabet, augmented with epsilon. Okay. So in other words, it will return an ordered pair, two factors, A comma B, if you like. And the first member of the ordered pair will be the next state, Q, and the second member of the ordered pair will be what? So that's the symbol of your stack alphabet that is to be put on the top of the stack, I guess. Okay, it's still a bit fuzzy on whether you're reading the stack, writing the stack. That will become clearer as we get into it. Anyway, for the formal definition of the range of the transition function, your delta, is this. Okay, so it too is a Cartesian product, but just of two sets. So the set of states and the stack alphabet augmented with epsilon. Okay, so Q cross, so the cross product, if you like, or vector product, or Cartesian product of Q cross gamma. Right? Okay, so we're getting there. So we've now done the formal definition of the transition function, which is the core, the main part of the definition of an automaton. It's the delta, the transition function part. Okay, now you remember earlier from the previous session that we'd be concentrating from now on non-deterministic PDAs, because there's a difference. Non-deterministic PDAs are more powerful than deterministic PDAs, and they're not equivalent. Those two, the non-deterministic PDA and the deterministic PDA, those two are not equivalent, because the non-deterministic PDA is more powerful. It can recognize more languages. We did that in part of the previous session. Okay. Now, okay, so we're now talking about non-deterministic PDAs. And what's the essence of non-determinism? Well, you can have more than one next state. Okay, you can have, in this case, more than one next move. And remember, a move being two things: the next state and a symbol from your stack alphabet that you'll do something with, presumably write it, push it onto the stack. Okay. Right. So you could have several next moves with a non-deterministic PDA, and so that means that your delta function, what it delivers is not just one ordered pair. It needs to deliver, in fact, a set of ordered pairs. So the range, strictly speaking, of your PDA, a non-deterministic PDA, is in fact the power set, P, the power set of this Cartesian product. Remember, Cartesian product is just a set. Right? It's a set of ordered pairs. Yeah, where the first member of your ordered pair is a state, and the second member of your ordered pair is a symbol from your stack alphabet. Okay. And remember what the power set was? It was the set of all possible subsets of some set. Well, the sum set here is the Cartesian product. So the range then is the power set. So what the delta function, transition function, can deliver is a set of ordered pairs. You know, a whole bunch of them. Right. So this then is, that's the heart of the definition of our PDA, the transition function. So now we're ready to give a formal definition. So definition 2.13, 13th thing in the chapter 2. And this time it'll be not a 5-tuple but a 6-tuple, because we've got an extra alphabet, the gamma, the stack alphabet. Okay. So the formal definition of PDA, push down automaton, is now a 6-tuple. And the other things are pretty much the same. Well, that'll be new, of course. Now the delta function will be new because it'll be of this form. Right? So we're taking it like a triple Cartesian product and mapping it to a double, well, a single, sorry. Well, this is like a double. Do you concentrate on the number of sets or the number of operators? Well, here you have a Cartesian product of 3 sets. Here you have a Cartesian product of 2 sets. Put it that way. Okay. So you have this 6-tuple, the 6 items in your list. That's what a 6-tuple is. A k-tuple is just a list of k things. Okay. First thing, Q, well that's the same, that's just a set of states, nothing new there. Okay. 2, capital sigma, that's the input alphabet in your input string, nothing new there. Capital gamma, the third thing here. Now that is new, that's the stack alphabet. That's the set of symbols you allowed that you can push and pop onto your stack. Right? So that's new. And the transition function we've just been doing here, so your domain, this more complex Cartesian product of 3 sets, and it maps into the range, which is the power set of this Cartesian product. Now let's interpret that physically, sort of intuitively, rather than abstractly mathematically. What's this transition function doing? Well, it's looking at the current state, it's looking at the current symbol on its input string, and it's looking at the symbol at the top of its stack. Okay? Now on the basis of those 3 things, it makes a decision. That's what transition functions do. Okay? And it decides on the next move. And the next move will be like the next state, and the symbol that it writes, if it does, onto the top of the stack. Now I'm getting a bit more specific now. Alright. Now 5, the 5th thing, that's just the start state. That's Q0, so nothing new there. And 6F, which is a subset. Not necessarily a proper subset. Oh, does that make sense? I've not thought about that before. Anyway, so F is usually a subset of Q. Okay, so the set of except states. So nothing new there. So the only stuff that's new is this and this. The other 4 are the same. Alright. Okay, now I have a sort of formal definition of the computation. How does a PDA compute? So So here's our 6 tuple for this machine M. It's a PTA. And how does it compute? Well, it computes in the following way. It's said to accept a string, and that's what PDAs are trying to do. They're trying to recognize a language, in other words, to accept or reject the strings of that language. Okay, so it accepts an input string W if, and then so let's write this input string as W1, W2, dot 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 WM. You can't see it's on the next board, next square in the next session. But W is your input string, and it consists of symbols from your input string alphabet, sigma, well, augmented actually, sigma suffix epsilon. So this W could be just epsilon, just the empty string. And so the W in general will be it'll be W1, W2, dot 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 WM. So in other words, just a string of symbols from your input alphabet. Okay, where WI belongs to your augmented the augmented alphabet of your string symbols. Alright, well, if I go any further into the next line of the next session, so I'll stop there.